This session is very, very important, very interesting for me because I don't know if you know, but we do a series called Datadog. Datadog is a series of events that we do online, live, but only online. We've been doing I think 30 sessions so far. And the idea of these sessions is that we invite engineers working every day on building Datadog itself to tell us about something that they're solving, like something that they're using as a tech, how they're using it, maybe some incidents that we solved. And we basically go online live on those. And we take a lot of questions from the audience. We are doing live online as well. So we are on the live stream. So if you're watching the live stream, we will take questions as well, both from the audience and here live in London and also online. So this is the first time that we do one of these episodes with a live audience. We are here on Datadog Summit in London. And if you want to watch this one or any of the previous episodes, they are all available on that website, datadogon.datadoghq.com. The episode today is going to be about stateful workloads on Kubernetes. So my name is Sara Pulido. I was here this morning, so maybe you already seen me. I'm a staff developer advocate at Datadog and one of the co-hosts and co-organizers of Datadog. So if you have any feedback about the series or if you have any topics that you want us to cover on a future episode, please do reach out. But the important people today here are Edward and Martin. Edward, do you want to introduce yourself?
Hi, my name's Edward. I've been at Datadog for about 2 years now, and I'm a manager on the team that manages Postgres at the company.
Martin?
Yep, I'm Martin. I've been at Datadog a year and a half or so, and I'm an engineer on the team that operates Kafka.
Good. So usually what we do when we start this episode is to talk a little bit about the scale that we run on, because some of the decisions on how we build Datadog are based on that scale. So Datadog currently has more than 27,000 customers. As you know, we are an observability platform, so we ingest telemetry data from all those customers. Those adds up to millions of hosts. That basically translates into tens of trillions of data points that we have to ingest per day, and we have to process, so we are able to make use of those. And all of this we run on our Kubernetes Infra. Our infra in Kubernetes is very big. We have thousands of clusters. Many of those clusters have more than 1,000 nodes each that basically translate into hundreds of thousands of pods. And more importantly, we do this because we also run those on different public clouds. And we've been on Kubernetes for about six years, more or less now, maybe a little bit more, 6, 7. But when you talk about people running stateless applications in Kubernetes, they're that's easy, that's how containers work, they come and go. But when we move to stateful workloads, things get a little bit trickier. So I would like to start this by asking both Edward and Martin why running stateful workloads in Kubernetes has this concept of being a little bit scary.
Yeah, basically we're just terrified of losing data. That's the one thing that we can't do when running these services is lose data. So it's
let's not do that.
Yeah, exactly.
Yeah, agreed. Data loss is terrifying. I think also Kubernetes took some time to be ready for stateful workloads. It initially launched without support for it. And it's taken some time to shed that reputation as being stateless only, but I think it's very much ready for stateful and has been for a long time now.
Yes. Yeah, I think that concept has stayed a little bit on people's mind for a while, but we will try to convince you that actually Kubernetes is now well ready for this. And we are going to do that with 2 use cases. Not we run more stateful workloads in Kubernetes, but obviously with Edward and Martin, we had to have the opportunity to talk about these 2 specific, Kafka and Postgres. So just let's start by giving a little bit of overview of what is Kafka for people who may not know.
Yeah, so Kafka, you could describe it as a distributed streaming platform. It's basically like a way of like storing data in an ordered fashion and sort of building stuff to manipulate that. What people really like about Kafka is that it's the bottom point here, it supports high throughput and low latency workloads. So the protocol is like really optimized for moving data like through Kafka with like minimal overhead. And like another thing, obviously, is that it runs as a cluster, so it can offer like high durability and high availability. So you can build like a very reliable, high throughput streaming service on top of Kafka.
Cool. So Postgres, I know.
Yeah.
What about
Yeah. Postgres is a relational data store based on SQL. It's open source. It's actually been around for something like 35 years, so quite a while. It's a very mature product at this point. It has a single leader architecture, which means any writes are going to that one leader at any moment. It's also possible to have multiple leaders, but that's not something that we do and not something that we'll talk about today. Something that we really like about it is that it's super extensible. So there's lots of extensions. There's a really rich ecosystem there. The protocol is very well described, which leads to a very rich proxy ecosystem as well. And we'll see that that's one of the benefits that we're using at Datadog.
Fantastic. So yeah, when I saw that Postgres was from 1989, for me it was like, I thought it was like maybe 20 years ago, but not 35, definitely. So for those of you who are on the live stream, by the way, if you don't have to wait until the very end to put your questions in, you can use YouTube comments or LinkedIn comments, and we get there at the end. We will make sure that we have enough time for questions at the very end. So we are going to make those examples, but a lot of the things that we use at Datadog to run those stateful workloads is common infrastructure that we have. So let's start by talking about those common things before we dive into the specifics. And one of the things that I want to make clear, we wanted to when we were preparing this, is that many of the things are just normal Kubernetes abstractions. So for example, stateful sets and persistent volume claims. Martin, do you want to give an overview?
Yeah, definitely. So there are like, Kubernetes itself is very extensible and some people do this differently, but at Datadog, we're actually just heavily using the basic primitives. So the first thing for a stateful system on Kubernetes is to use a stateful set. So this is like deployments, a grouping of pods, but the key thing is that each pod is given a persistent identifier, like pod 1, pod 2, pod 3 here. And this is helpful because it makes it easy to match like a volume to a pod. So what is a volume? So in Kubernetes, there's a concept of a persistent volume, which can actually mean like many different things. It could be a volume, which is like the local disk on a Kubernetes node, or it could be a volume, which is like cloud block storage, for example, EBS. All those different things could be PVs. And there's also this concept of a PVC, a persistent volume claim, which kind of represents an application's request for storage. It's kind of useful to decouple these things. And the sort of workflow here is that the pod creates a PVC which gets bound to some persistent volume which meets its requirements. And it can sort of use that. And yeah, we'll see some examples of that in a moment. Yeah, so another thing that we're using heavily at Datadog is this concept of a node group. So this is a custom resource that Datadog uses internally. And what it basically is an abstraction over an auto-scaling group on like the various cloud providers. One of the things that we use Kubernetes for is an abstraction over the different cloud providers. So this is really helpful. And this kind of like manages like the sort of like all the auto-scaling that you'd want, like nodes just come when you ask for them. It's really nice. We don't have to think about it too much. Yeah, maybe an example of how we sort of use these. So you can see here that we have an example where we have like an instance type, so m6g.xlarge. As someone on the Kafka team, like I'm probably like, I want a machine where she's got good enough CPU, a lot of throughput, and a lot of storage. So I might like look through the sort of like what's available and be like, okay, m6g.xlarge, that's got decent CPU, I'll take that. The other sort of key thing is that we can say how much storage we need. The useful thing here is that like this abstraction works in a different way over different providers. So we can just basically say requirements for machines. This allows us to do things like t-shirt sizing, where we can like have a notion of like what is a medium-sized machine on different cloud providers. Yeah, we can sort of say exactly what we need in terms of storage. Next slide, please.
Yes. So I think it's very interesting to see that one of the things that made us switch to Kubernetes was that it's very extensible through this API. Everything's API-driven. So you're able to do these custom resources that allow you to build abstractions that suit your use case. So for PVs, you're able to actually have them as local storage in the node. And we do that, but we also do remote storage. So what are those two differences between one and the other?
Yeah, so I think this is like quite a sort of like fundamental thing, distinction, but there's a lot of like pros and cons, and they kind of come in pairs. So the first one is like local storage can be cheaper. So certainly like some cloud block storage has a reputation as being expensive, and it probably is if you're storing a lot of data on it. But I say can be here because it really depends on the workload. Smaller storage footprint things might actually find remote storage cheaper in some cases. The big one, I think, is like the failure modes. Like if you're using local storage, there's obviously like no network between you and the disk, which is great. On remote storage, like you have to think about the cases like what happens if the disk becomes unavailable. It's more frequent. Another thing that Edward will go into more detail on, but we sort of regularly replacing nodes, by which I mean Kubernetes nodes. And if you're using the local storage on that Kubernetes node, then you have to somehow get the data back when you replace it. Whereas with volumes, you can just reattach them, like a remote storage volume, you can reattach to a new machine, and that's very nice. Kind of like the extreme case of this previous point is like, what happens if you lose all Kubernetes nodes in a cluster? It can happen. So the sort of there's a sort of no separation of failure domains with local storage. Like you lose all your nodes, you lose all your disks. That's really bad. If you've got remote storage, then these are different problems, and you can sort of reattach all your storage to the new cluster, so you're only worried about availability in that case. Finally, it's a bit more flexible having these sort of decoupled storage and compute things. With local storage, there's a pretty limited list of VMs that you can actually use in each provider, whereas if you're using remote storage, you can really be like, I don't know, you've got much more options when it comes to like saying, I want this amount of CPU, this amount of storage. And finally, performance, which I put a kind of question mark next to, because I think it kind of like, remote storage again has a reputation as being less performant, but one, I think it has improved a lot, so that might not be the case anymore. And another thing is like you really need to benchmark it. Kafka uses disks in a very specific way, which means that this isn't really much of an issue for us, but it could be different for different workloads. So I think you just need to benchmark, really.
Great. We've talked about node replacement and how it is different from local and remote storage. But at Datadog, we don't do this just when it fails. We have something called node lifecycle automation that replaces nodes that are older than an amount of days. That means that at size, we are replacing thousands of nodes each day, and that has some implications for stateful teams like Postgres, I guess.
Yep. Yeah, for all the teams. So usually, if you're running in the cloud, if you're running in a cloud, you're going to be used to nodes coming and going. So if you run for long enough, maybe like a node will fail every couple of days or every couple of weeks or something like that. The benefit of node lifecycle automation is that it causes those nodes to fail every couple hours, maybe. So you really get good at handling a node failure. And so for that, it causes, there's two cases that we have to deal with. There's this case of a node failing when we didn't plan for it. This is like the node crashing, the node getting replaced by the cloud provider. We don't get any notice on that. So kind of like from one moment to the next, the node is gone. And then the thing that we care about at that point is how long is it going to take before we have a replacement node up and running. And that node is really part of the cluster and serving requests. And with local storage, the big factor that makes that difference is going to be how long it takes to get the data back onto the node. So one of the ways that we optimize that for Postgres is by just backing up the data very often to cloud blob storage, and then when the replacement node comes back, pulling that back onto the node. But like Martin mentioned, that takes time. You're copying data back and forth. So if you can do this, if you have remote storage, that's obviously going to be quicker. Then you can just reattach the volume. If you're using NLA, the automation will actually tell you, hey, I would like to replace this node. Can you please prepare it so I can have it? And then what we do in those callbacks would be something like triggering a leader election to make sure that node isn't the leader of the cluster at that moment. Maybe we trigger a backup as well so that we make sure that the data in the backup is as fresh as possible. And then we tell the automation, yep, I'm done. And then we can kind of swap the node really quickly. And kind of with that notice, then the amount of time where the node is actually, or where the cluster is impacted by the node replacement is super short. And which is good because we do it hundreds and hundreds of times per day.
So you have to better get your things together. So for example, no lifecycle automation is something that our compute team offers. So many of the things that you do are based on the things that the compute team offers to the different teams. And one of the latest things that they've been working on is this concept of regional versus zonal clusters. You can go there.
So here we see kind of like an idealized, simple version of our application. It's running in all the availability zones. Most of the cloud providers have these availability zones. Like Martin mentioned, these are our failure domains. So you wouldn't want a failure to go beyond one of the availability zones. And if we drop our application into a Kubernetes cluster, you can see this Kubernetes cluster kind of it stretches across multiple availability zones, which should be kind of like the first indication, like, maybe that's not good. So you can imagine here, if something happened in our Kubernetes control plane, like Martin mentioned, maybe it kills all of the nodes in the cluster. And if our app is deployed in this cluster, that means that our app has been killed across all three availability zones. If we're using local storage, that basically means data loss, which means lack of availability, lack of durability. This is kind of like the worst case scenario. So the way we avoid this is something called zonal clusters. You can see from our app perspective, it looks the same. Like each application is running inside a single availability zone, but the world around it is kind of different now. So each Kubernetes cluster exists in one zone, and each zone has one Kubernetes cluster. And you can also see kind of visually that nothing's crossing these dashed lines anymore, which means that if the control plane dies in this case, it's going to kill all of the nodes in that Kubernetes cluster, which kills one of our application pods, but we've still got the rest of the pods running there. And because we design our application for an availability zone disappearing, we've still got our application, which is continuing to serve traffic and no data loss, maybe like an availability blip, but that's it.
Sounds good. So all of that, it was a little bit of introduction of all the common base for any application at Datadog that we have. But now I'm going to pass the clicker to Martin, who is going to go a little bit deeper into the specifics of Kafka.
Okay. So first, a little bit of history, I guess. Kafka was probably, this is rough for the earlier history, but Kafka was probably been in use at Datadog for about 10 years. And I'd say it was sort of like very widely used by pretty much everyone since 2017. So we had the Kubernetes migration, and I'd say by like 2019, like there's a lot of like big applications using Kafka and Kubernetes at Datadog. And I'd say the story since then has mostly just been like increase in scale. So we're sort of like several hundred clusters. We have to like have lots of like good automation at that sort of scale, like so sort of auto scale and failure handling. That's been a lot of what we're working on there. More recently, we've begun adopting like tiered and remote storage. So I'll talk about these more later on, but this is more about like decoupling the compute and storage that we mentioned briefly earlier on. So yeah, if you're running a Kafka setup anywhere, well, like modern Kafka, you can use Craft, but we're still using Zookeeper-backed clusters in most cases. So you need a Kafka cluster and a Zookeeper cluster. And we're using just basic stateful sets for both of these. The Kafka cluster stores metadata in the Zookeeper cluster. I mentioned the node groups earlier on, and we sort of have like dedicated node groups for Kafka. We have requirements like what's a like medium-sized machine on AWS, for example, and the Kafka cluster, as Postgres it will request node from this node group, and they'll just magically appear, which is very nice. Another thing that I won't talk about much, but it's actually really important, is every cluster at Datadog has these like tool deployments alongside, which is basically automating a lot of the operations. So things like auto-scaling, which actually interacts back with the node groups and the auto-scaling for the underlying node groups, and various like operational and resource management APIs. So I'd like to go into some detail about how exactly we get persistent volumes for our Kafka brokers. So Kafka brokers are like the stateful part in Kafka. This is where the data is stored. So you're going to need a volume for a broker pod. And we're just using the sort of basic like stateful set ideas here. So first off, we have a node affinity, which says this node must be scheduled on Kafka medium node group. If it's that node group's not big enough, the node will automatically be added. But once it's there, the pod is scheduled on the node, and the persistent volume claim will bind to the persistent volume on the node. Yeah, one thing to like sort of notice here is that the persistent volume claim is like related to the name of the broker pod. That's not a coincidence. Like that's actually key to making sure that this like identity survives pod restarts, for example. Cool. So once our broker pod is on the node and persistent volume claim is bound to the persistent volume, the broker can start running and it can join the Kafka cluster. And when it's joining a Kafka cluster, it'll need a broker ID, which is like how the cluster is going to refer to that. And again, this is also derived from the sort of pod name, which is a stable identifier in a stateful set. So here, like broker ID might be 0 if the broker pod was ordinal 0 in the stateful set. So this setup, which is what we sort of historically used, has like a couple of like really nice properties. So like one is that like node replacement is completely automatic. So if your node fails, like the persistent volume is going to go. So the persistent volume is deleted, PVC becomes unbound. The pod is just automatically scheduled on a different node in the same node group, and we go through the same process. And now the broker pod enters the cluster. It doesn't have any data at this point, but Kafka replication will just automatically mean that it catches up data from its peers. So that's nice and automatic. And somewhat related, like for a roll and restart, where the node stays, but just the pod is restarted, we know because the persistent volume claim is bound to the persistent volume on this node, the broker is just automatically going to get rescheduled there. And all you have to do is like a very small amount of catch up from its peers to catch the data that it missed while it was down. So roll restarts could be pretty fast. There are downsides though. So the big one is sort of like the time it takes to replace a node. So we mentioned that it's having to like replicate data from its peers. This can take like many hours in our sort of like biggest production clusters. We've got 2 examples here, 2 node replacements. It takes about 10 hours in total. So yeah, that's not ideal. Another thing that you have to be very careful about So in most cases, this happens automatically. A broker fails, the Kafka cluster detects it, it kicks it out. When that broker re-enters, it's just a follower for everything. It doesn't have any leadership responsibilities, and that's all fine. There are definitely some strange edge cases, which we sort of find in chaos testing environments where this Kafka doesn't detect a failure and doesn't successfully demote from leadership. So you have to be very careful that this doesn't happen, because if the broker enters the cluster as a leader with empty disk, then the authoritative state of the data is that there is none, and you've got data loss. So yeah, you need to explicitly guard against that potential edge case in Kafka. Finally, there's the cost aspect. So we are sort of forced to use storage-optimized machines on cloud providers because we need enough disk to cover however much retention we need, but 99% of the time, our applications are only reading the last few seconds worth of data from Kafka. So it's very wasteful to spend so much money on this local disks that you're barely using unless there's some incident where you need to do a backfill. So one of the things that we've been adopting to address this is tiered storage. So the sort of idea here is, well, this old historical data that you're not reading so much, why don't you put it somewhere cheaper? So that's exactly what tiered storage is. It's a relatively new feature in Kafka itself, but there have been sort of implementations of this in various forks over the recent times. You keep your sort of hot data, could be say 2 hours worth, or possibly even less if you want, on your local SSDs, and the historical data you put in S3. And there's plugins for different cloud providers, so you can use this across clouds, and it's not a big change to Kafka. It's basically just more performance tuning, but API-wise, there's nothing to change. So yeah, the major benefit is sort of improved operations, like these node replacements, which I said could take hours and become much faster if you have most of the data in S3, because the data that's in S3 you don't have to replicate. It's just, you just pick it up as you need it. And you have opportunities for cost savings by aligning the usage with this aligns more with the usage patterns where this old data is rarely read. And finally, even just from a feature point of view, we'd have users who want to set really long retention, maybe a week, but that was impractical before because just the storage costs would be astronomical. But now we can do that. It's relatively cheap to just increase the retention in S3. So here's a quick graph of sort of faster node replacement. This is sort of a 2 hours down to 25 minutes once you start using tiered storage. This is from our staged environment, so the amount of data is not actually all that huge compared to some of our production ones, where the improvements would actually be probably bigger. Okay, nothing's ever free, I guess. So there are new failure modes. One is cloud storage can go down. It's rare, but it could in theory happen. And if that does happen, then you've got some problems where you can't upload files, so you're probably filling up local disks. You've probably got a nasty incident, so you do need a mitigation strategy for that. Another thing is, so you need to be sure that tiered storage traffic is background traffic, because serving your customers' read and writes is always the most important part. So yeah, this needs to be managed somehow, so you need some sort of throttling mechanism. And finally, in the rare cases where you do need to read historical data, this is by design going to be slower in this approach, but you do need to, you don't want it to be terrible, so there's some work to do to tune this to make it reasonably performant. So yeah, so that's a big thing that we've been working on. There's a couple other things which touch with our interactions with Kubernetes right now. So we're also sort of evaluating remote storage. So we're using this in some cases for smaller workloads already. But for larger workloads, it only really becomes an option once you're using tiered storage for cost reasons. You can't store very large amounts of data in, say, EBS without it being too costly, but the two together sort of might be feasible. And this kind of opens up a bunch of the benefits I said about using remote disks versus local disks. Another thing is sort of multi-tenancy. So you have kind of two options for this when you're running Kubernetes. You can do multi-tenancy at the Kubernetes level. Many Kafka brokers on the same node. We're currently only using one because we're using local disk. Although we're probably going to go the opposite way and do multi-tenancy at the Kafka level instead, but that's still work in progress. Finally, we're regularly doing chaos testing, so we're using Chaos Controller, which is something that Datadog has open sourced, I believe, for just injecting faults in your Kafka clusters all the time. So we're doing that regularly and looking at large-scale failures like an AZ loss or a K8s cluster loss and seeing if we are at least reasonably resilient for those. Yeah, I think that's all I had.
Cool. If you're interested, historically, have we been running Kafka in Kubernetes for a while? Actually, our first ever Datadog episode was fully on Kafka back in 2020. The team was already running in Kubernetes. And I think it's very interesting that we got both Martin and Edward to see the difference in maturity. Because as Martin mentioned, Datadog has been running Kafka in Kubernetes almost from the very beginning. Postgres, as we will see in Edward's section, it's a little bit different. They're newer in this Kubernetes journey. So Edward is going to take it away from here and tell us about Postgres.
Thanks. So we've had Postgres at Datadog basically since the beginning. So 2010, we were running Postgres inside of virtual machines on EC2 at that point. And that worked for us pretty well for a long time. Basically a decade we were running with that kind of that architecture. Martin mentioned 2019, we started moving everything from virtual machines into Kubernetes. In 2021, we were also wanting to move out of virtual machines, but we didn't quite trust that we could run this stateful workload inside of Kubernetes at that time. So the move that we made was into cloud-managed data stores, so RDS or Cloud SQL, something like that. Pretty quickly, we realized that instead of kind of not having to deal with any of the stack other than Postgres, we actually had to deal with a bunch of different stacks. So kind of each one of these cloud-managed Postgres offerings had their rough edges. And now we had to be an expert at all of those rough edges. So pretty quickly after we saw that, we started planning our move into Kubernetes. So 2022, we had our first clusters running on local storage in Kubernetes. And now in the past year, we've been exploring using remote storage in Kubernetes for similar reasons that we'll talk about. So why did we want to do it on Kubernetes? Like we talked about a couple of times, Datadog's pretty good at Kubernetes in the meantime. It's been 5-6 years, so we know how to do that well. Having Kubernetes as an abstraction is really nice. You know, we don't have to deal with all the stuff further down in the stack. We just talk, stateful sets and persistent volumes and that kind of stuff. Being able to have consistent operations across all of the cloud providers is super nice. Just having to do one type of operation and do it wherever you want, really great. And the flexibility is nice. We can set the settings we want. We can use the extensions we want. We can use the versions we want. It's all on us. The downsides are it's all on us. So we have to do these operations, and I'll mention some of those in a bit. So here's our architecture, and I'll talk through each individual piece. So in the middle, this is kind of like the pure Postgres part of it. You see, like I mentioned, there's a single leader, the current leader. We have a bunch of warm standbys, one of those in each availability zone, and those are kept up to date with replication, so streaming replication to them. In addition, we've got read-only replica pools that are also kept up to date with replication, streaming replication. We only have those for clusters that are big enough to need it. If possible, we can sometimes just work with a single leader. We also use Zookeeper to store metadata about the cluster. That's done using a package called Patroni, which stores cluster state and cluster configuration into a pluggable configuration store. In our case, it's Zookeeper. So for each Postgres cluster, we have a Postgres cluster and a Zookeeper cluster that we're running. For backups, we put both kind of full data, full cluster backups and write-ahead logs into cloud blob storage for Postgres and also for Zookeeper. And then for the query side of things, We've got a proxy in front of all of these leaders and warm standbys. The way this works is that Patroni gives a health check API to the proxy. So all of these leaders and warm standbys exist in a single backend pool of the proxy, but only one of them is healthy at a single time. And that's the one that receives requests from the application through the proxy. On the read side, we also have a proxy in front of them. The health check on that is done using the replication lag. So if a read replica is too far behind the leader, then it'll get pulled out of the backend pool until it gets a chance to catch up. Yeah, so that's the whole architecture. Each one of these white boxes is a Kubernetes pod. So let's dig into what a Postgres pod looks like. So inside of a single pod, we've got a single container. Inside of that single container, there are a bunch of processes. So the first process is the Postgres postmaster. This is the part that actually opens up a socket and receives connections from the applications. It hands off those connections to a background processor that processes it. There's a bunch of other workers like auto vacuum worker, wall sending, stats collecting. All these processes are running in the container as well. And then one more process is the Patroni process. What this is doing is kind of continually taking the cluster state and reflecting it into the Zookeeper cluster and checking to make sure that all of the nodes in the cluster are still accessible. If it notices anything is up in the cluster, then it triggers a leader election. It also has this HTTP API where it makes this status available to the proxy. So we've got the pods. Let's kind of drop them down onto some nodes. And so this slide tells us how we distribute nodes, how we distribute the pods in the nodes in our clusters. There are two dimensions here. On the left-hand side, you see this local and remote storage. This is similar to what Martin talked about. On the top, you've got dedicated and shared nodes. And the architecture that we used when we first started was running on dedicated nodes with local storage. We thought this was going to be the most cost efficient as well as the most performant. Yeah, that's not necessarily always the case. The way that we're moving now is to use remote storage almost in all cases if the cluster supports it, and to use usually dedicated nodes. For smaller clusters, we can afford to pack multiple clusters onto a single node, or even mix it up with completely unrelated data stores.
Before you go into operations, I wanted to ask you or clarify for the audience, Patroni is an open source project that,
yes. Yep.
that allow you to run.
Yeah, Patroni is an open source project. It's how you do high availability with Postgres. There are other ways probably, but this is the one that we use and like. We like it so much we've created some open source extensions for it. We've pushed back a couple patches. Yeah, it's a great project.
Cool.
Yeah. Yeah, so let's talk a bit about some of these operations that we have the joy to be able to run on our cluster. Backups is a really common one. So we're pushing backups, and so these are full data backups of the data in the cluster, as well as write-ahead logs into Cloud Blob Storage. And the frequency that we do those backups and pushing the walls is a tunable knob that we can use to determine how fast a replacement node comes back after it's crashed. So if you're doing them very often, the data is going to be super fresh in the backup, and a node is going to be able to come up pretty quickly once it comes back. The downside of that is that you're doing a lot of processing and doing backups and doing checkpoints on the write-ahead logs, which is CPU that you're using and not using to serve requests to your users. So that's kind of the trade-off there. Some other cluster lifecycle operations that we do, major version upgrades, those are on us to do now. Migrations to Kubernetes. Something I didn't mention back in this timeline view is that none of those points are actually like fixed points in time. They're all like smeared over years. And so these migrations into Kubernetes from cloud managed storage is also something that's ongoing. And then there's also table split outs. So if a database ever grows bigger than it should be, and we want to pull some tables out and put them in their own database, that would be this table split out case. And all three of these operations are driven using what we call blue-green deployments. So, and for example, a major version upgrade would be we take the cluster, we duplicate it, we upgrade the new cluster, we redirect traffic to the new cluster, and then we decommission the old one. And that's how we do all of these kind of operations. So that's the state as it is right now. That's what we have running for the most part in Datadog in production. The future that we see for Postgres is improving this proxy story. So we have a proxy, I mentioned it a couple times, it's in front of the leaders, it's in front of the replicas. It's used to redirect traffic when doing these blue-green deployments. In addition, we have PG Bouncer, a common connection pool. So all these are proxies, and they're all different softwares, different services that we have to run, that we have to know, that we have to understand. So we see some real benefits to our architecture by replacing all of these with a single proxy that we've written, and kind of getting that whole proxy behavior, as well as some interesting features as well, as such as authentication, really nice. We don't have to deal with passwords anymore, which is amazing. Automatic traffic routing, only sending selects to the read replicas, everything else going to the leader. Integrated caching, we're Datadog, so we want best of class observability inside this proxy. So yeah, that's what we're working on now. And this is where we see the big benefit coming to our application developers by having this nice proxy.
Cool, thanks a lot, Edward. So we are going to, we've covered a lot. Things that are common, things that are specific. We are going to take questions just after doing a little bit of summary of some of the takeaways. So if you're in the live stream, please put a comment on YouTube or LinkedIn, and we will be answering your questions. If you're here at Datadog Summit in London, we will pass a mic around for questions. So we want really to make this as conversational as possible going now in the next 15 minutes. So I will pass this to Martin for some takeaways.
Yeah, sure. So so I think the first one is Kubernetes is definitely data ready. I'd say it has been for a long time. But you do need to understand how things work. You need to understand the edge cases, and it might be specific to your data store as well. So we talked a lot about what storage you use. Local storage is cheaper, or at least it can be cheaper, but it will require sort of more operations overhead. So there might be a benefit to offloading storage if you can, for remote storage, for example. Something that I think is important to keep in mind is that Kubernetes itself is a failure domain. You can lose an entire Kubernetes cluster. So yeah, what happens in that case is something you need to keep in mind. And finally, we at Datadog are very lucky. We've got a big compute team who provide a lot of useful abstractions, a lot of useful multi-cloud abstractions. So yeah, we're able to rely on a lot of common tooling from our Kubernetes team, which is really helpful.
Yes, good. So thank you. We are going to take it now for questions. Thanks, Edward and Martin. That was very, very insightful. So if we have any questions from the audience. So anyone? So I have a question on why people think about questions. One of the things that people do with stateful sets in general, anything in Kubernetes, but there are especially on things that require a lot of operations, like stateful sets. People rely a lot on open source operators that people have built and trying to mimic this expertise of how to do all these operations in something that is more or less automatic. Any reason why or why not would you use an operator?
Yeah, when we were first planning our migration into Kubernetes, we evaluated all of the possible operators out there. There's a bunch of really nice ones. They all had a couple things that didn't make them fit either our scale or our particular, some of the things that we use. We use replica groups of read replicas. That wasn't available in some of the operators. So there was always something that didn't fit. The multi-cloud aspect or the multi-cluster aspect, if these zonal clusters could also be something that I think very few operators support out of the box. So in the end, we just wanted to own, if we were going to own everything, we wanted to really like own it all.
Really own it. What about Kafka?
Yeah, so I'd say in Kafka's case, since we started so early, it probably wasn't so much of an option at the time. Like now there are some very nice Kafka operators, for example, StreamT out there in open source. I think given that we've been doing this for so long now, like migrating to StreamT, it's not particularly appealing for us because we've built a lot of the things ourselves. And a lot of the challenges that we're facing now are like, because we have so many clusters and we need to coordinate across clusters, and also because our Kafka clusters are not necessarily scoped to a single K8s cluster as well. So some of these things that don't fit in the operators now, but I think a few years ago we might have thought about things differently, but where we're at now I don't think makes much sense.
Good. Any questions from the audience? Yes.
Yeah, you talk about the tiered storage. Does that span across things like FSX and Glacier and?
Yeah, so for now, we're just using basic S3. But I think there is an option to, it's completely pluggable. So you can, actually, so from Kafka, you can say like what storage you want to send it to, and you like develop a plugin to put it there. So for tiers within, sorry?
You can write exclusion rules and...
Yeah, it's basically completely pluggable as long as you code to the interface for how files go from Kafka to where you want them to go. Yeah.
It sounds like multi-cloud is a huge advantage of this approach with Kafka and Postgres. For an organization that's single cloud, do you think it's still an approach that could make sense?
Very good
question.
Yeah, totally. Yeah, I think it would. I think probably running your own Kubernetes clusters then doesn't make that kind of sense. But like the basis that that Kubernetes provides is just a really nice abstraction. At previous companies, I've used it as to not get tied down to a single cloud provider, to have that be like your abstraction. So I totally think it could still be valid if you're already doing Kubernetes. I wouldn't start doing Kubernetes for stateful stuff necessarily.
Yes. Yeah, I think that abstraction layer when you're multi-cloud is even better, but I think it's even worth if you're already have some expertise into Kubernetes. Any other questions over there? Claire?
You mentioned at points you had some stateful workloads that was partly on VMs and partly on Kubernetes. Were there any challenges when you were like halfway through and some was on VMs and some was on K8s?
We didn't have any databases that were spread across VMs and Kubernetes. So when we decided to make that change, it was kind of like an atomic change for a single database. We did it for some big databases, so that atomic change was still a big operation, but we didn't really spread across the two.
Yeah. We actually have questions from the live stream. So talking about zonal clusters, making sure that keeping them in sync, how do you manage all that network traffic?
Yeah. So I guess there's two aspects to that. Like, so one is like configuration. So if you're spinning up like the same infrastructure on like 3 different zones, you need like some common way of doing that. This is something that we would code in our Helm charts. Like we would somehow parameterize what we deploy in the 3 different clusters in some sort of consistent way. So that would be managed through code. In terms of actually running it, yes, so there will be like things like cross-AZ traffic to consider. Although there are actually like different topologies. Like sometimes you might want to say like exactly what do I want to go across AZ, but right now if we're running a regional cluster, everything goes across AZ by default. And you can do the same thing if you're running 3 individual deployments in different zonal clusters. Like this could still be one big Kafka cluster replicating across different AZs, for example.
Yeah, it's the same thing for Postgres. Like in the end, like the picture looks the same whether it's regional or zonal. You still have pods running in different availability zones. The traffic is still the same amount of traffic. It's just kind of like the picture you draw on top of that is going to be a bit different.
Yes. Which reminds me that maybe we should do an episode on the networking layer that we have in our cluster, which the team owning that has been doing amazing work. Any other questions? Okay, I think we are good. Then thank you very much. Thanks, Martin and Edward.
Thanks.